So, good afternoon, everyone. So this is a talk on render pipeline shaders, or RPS. If you're not familiar with this, then great. This talk is for you. If you've already heard about RPS or tried it out, there's still some value here. Okay, so just to properly sort of introduce myself, my name's Gareth Thomas. I work for AMD, and I'm based in the UK, so you might not have worked with me, but you might be familiar with some of my colleagues. We've got Adam Zawicki, we've got Dawid, Marek, and Piotr, and Łukasz. So we've got quite a team in Poland as well, so you might find yourself reaching out to these guys. So our role is essentially to try and help you guys get the most out of AMD hardware. So, ping us for any sort of information on how the hardware works, the drivers, the tools, best practices, all that stuff. Okay, so we're here to help you guys. So, and a bit of background about me, perhaps. So, I've been a dev tech for about 10 years. I've seen a lot of engines and different technologies sort of across Europe and a bit of the US. And before that, I was a game developer. I worked at Codemasters for, again, over 10 years, sort of writing engine tech for Dirt and Grid, stuff like that. So I've kind of been on both sides of the fences. And then, probably like a lot of you, I've got my own sort of home hobby engine as well. So that kind of keeps my programming skills sharp. And I've actually integrated RPS into that. So I've had good sort of tested all the corner cases of this. So while I haven't written this SDK, I've certainly used it in anger, and I'm very confident and sort of passionate about the tech. I think this is really cool tech. So hopefully some of that enthusiasm comes across today. So the plan, I've got about 45 minutes to talk, I think, and then we'll take questions at the end. But I thought we'd just look at some of the challenges that you guys are facing on modern GPUs first, before we then start talking about the concept of frame graphs or render graphs, however you want to call them. Then we'll look at the SDK a bit, and then look at some results and draw some conclusions. So, actually, before we kind of dive into things, I was thinking about what makes a good game architecture. So I had a little think about it. And so this is my list, and you might have your set of sort of metrics as to what makes a good engine, but happy to discuss that at the bar over a beer later. But so the obvious things first are like, does your game engine make great games? That's kind of important. As a graphics guy, I want my engine to look great, and then obviously with the amount of content you now need to make a compelling game, and just the cost of that, you need great tools. So obvious stuff first. But then kind of with my sort of hardware hat on, I care very much about how efficiently you can run your game engine on the hardware, so on the CPU and on the GPU. And to give you a bit of insight into sort of our job, like we generally want you to be GPU bound, certainly at 4K, but ideally at 1080p as well. So not to belittle like the CPU work, but it's kind of almost easier to go wide on your CPU cores and get the bottleneck off the CPU, and you get good gains from that, compared to trying to optimize for the GPU. That is, generally speaking, a harder problem. So we always try and get you to go wide on the CPU cores, and then once you're GPU bound, then we can start looking at how efficiently you can feed the GPU, and that's really key to this talk here. And then there's this other aspect of your game engine architecture is how easy is it to add a feature to your engine? So we've been kind of a little bit in the trenches with this recently, sort of helping game developers add stuff like fidelity effects, super resolution 2, like the upscaling tech to game engines. And some engines it's easy, some engines it's significantly more work. And you can almost boil it down to the simple metric of how easy is it to move one pass before another. So you've got a post-process chain. I want to move one pass to another place. is it a single line of code to do that? Can I do it on the fly? Great if you can. Some engine architectures, you think, oh, that's going to take a week to get it right. And you've got to think, okay, well, that's when you're really fighting against the architecture there. So that's kind of that scenario where you think, well, maybe we need a bit of a refactor. But I bring this up because all these metrics that I'm thinking about, RPS can really help you with those. So kind of bear that in mind as we go through the talk. Okay, so challenges. I'll talk about 2 of them, and they're your challenges, but because we're here to help you, there are challenges too, so we're trying to solve these. The first one is kind of an obvious point, actually, but just GPUs are simply getting more powerful. Like if you look on the sort of the left here, you've got GCN1, and kind of it's going through the GCN generations. Then you've got RDNA and RDNA2 and RDNA3. The general gist, you can kind of see the trend where it's going here. And just to compare apples to apples, I've actually plotted, this is floating point single issue of floating point operations, because actually that sort of RDNA3 card on the end, the 7900 XTX, so on RDNA3 you can actually dual issue floating point operations per clock. So actually the teraflops is not sort of 30-ish, it's more like 60-ish, but just to keep my graph sane, just show sort of that. But you can kind of see the trend. Now, that is also then set against the backdrop that I think the consensus in the industry is that we've had 1080p and now we've got 4K. There's not this massive appetite to go to 8K or 16K. And even if we did, we've got really good upscaling technology to get you there. It's more now about the quality of the pixels and getting a more compelling experience at, say, that sort of 4K target. Which means that you're ending up putting more and more work onto the GPU. So part of this uplift in power and sort of performance of your GPUs is clock speed. So like GCN1 might have been sort of, it's about 900 megahertz, and then RDNA3 at the other end is kind of 3+ gigahertz. But the machines are getting wider as well. So again, GCN1 was like 2,000 SIMD lanes in the machine, and then RDNA3 is kind of 6,000 plus SIMD lanes. So that's great, and you can see the trend here, but it becomes more and more difficult to fill that machine with meaningful work, just as it is with CPU cores. You know, if you've got almost 100 cores on a CPU, it's really hard to fill them with sensible work. So that's the challenge here. And to kind of demonstrate my point, I've got this is an RGP capture of a game which I've kind of picked almost at random. I won't tell you what it is, but it's a great looking game written by very smart people. And it kind of has some interesting sort of, but typical sort of appearance to it. If you're not familiar with what this is, so Radeon GPU Profiler, it's like our sort of very useful tool, but what we're showing here is the frame from start to finish and the occupancy of the compute units, so how busy the compute units are. That top graph is how busy the machine is on the graphics queue, and then the sort of the graph pointing downwards is, it's on the same machine, but it's work issued from the compute queue, the asynchronous compute queue. And the color coding is such that it's yellow is compute work and compute shader, and then you've got the blue, which is pixel shader, green is vertex shader, and there's a bit of red there, which is ray tracing work. And then you've got the light blue bars, that's how long the draw calls are, and then the red lines are kind of the scope of barriers. So if you haven't seen it, this is an interesting tool, and we'll be looking at a lot of these going forwards. So yeah, this is typical now. This is going back to my point about how we're putting more work onto the machine. It's now stuff like particle systems or water simulations, or writing your virtual terrain texture, or even there's a bit of like BVH building there. you can see how these are kind of dispatch one by one calls. It doesn't run great on a 6,000 lane SIMD machine. So it has to be there because our GPU is going to consume this work later on in the frame. But it's interesting to see that this is very typical now, and yeah, it doesn't occupy the machine very well. So perhaps this can be rescheduled in some way. And then you've got areas which are good occupancy. Now, this doesn't mean that we can't optimize this. We absolutely can, but at least it's filling the machine. You know, and especially kind of, you've got this area here where you've got a bit of graphics work, but it's fairly low occupancy, but we've also got asynchronous compute work that's occupying the rest of the compute unit. So that's good. And then you've got areas where you think that like a 4K post-process chain should be really good for occupancy. You know, each target is like 8 million pixels or 8 million threads. But when you zoom in on it, okay, yes, you've got these kind of big workloads, but in between them, you've got these big gaps where we've got like we're draining the machine, we might be doing some low occupancy work, and then we're filling it again for the next sort of 8 million thread workload. So even here, you think under like ideal conditions, we could somehow squeeze a bit of performance out of this again. So the next challenge, it's probably one that you're very familiar with now, is this whole explicit API challenge. When I talk about explicit APIs, I'm talking about DirectX 12 and Vulkan, the ones where you've got to record your own command buffers, manage your own memory, and sort of transition your own resources. So back in the good old days, you'd have something like OpenGL or DirectX 11, where things were much, much easier. You had a single thread, and you just submit the draw calls on one thread. And then, again, going back to my point about how we want you to be GPU bound to alleviate the CPU bottleneck that might cause, we would spin up another thread in the background, like a driver thread. And your draw calls would actually not do very much. They'd just be submitting kind of packet information, and then the driver thread would be consuming that, building the PM4 packets and submitting those to the GPU. But the good thing about this is it's all on one thread. So the driver can look back in history of that frame and then decide where the barriers should go. And then the logic was complicated in the driver, but it would put in fairly good placement of barriers. So fast forward to DirectX 12 and Vulkan, and now, okay, so the work is still being submitted on the GPU in the same order, but perhaps with the complexity that you can now schedule it onto the async compute queue as well. But now you're building the command buffers, the PM4 packets underneath the hood, yourselves on different threads. And these threaded workloads could be kicked off in arbitrary order, which makes things a little tricky. So for example, for the blue workload, you don't know what the state of the resources are that you're going to be working on those, because you don't really know what or when the green and red workloads are going to be executed. And these different workloads, potentially completely different systems, they might be toggled on or off based on different configurations written by different people. It's very difficult to explicitly, perfectly set your barriers. So perhaps you could apply some like dogmatic rules where you go, okay, on my every command buffer I start with, I'm going to just set them into the read state. They're going to be in read state, I'm going to assume that. And then if I want to write to them, I'm going to transition to write to them, and then transition them back. The problem there is you just end up doing too many barriers. And this is the kind of thing you see when you've got too many barriers. It's just, we're not making great use of filling the GPU. And some of those barriers can be expensive, you know, and unnecessary. So you get scenarios like this where you're not getting really much useful work done on the machine. So yeah, placing barriers perfectly is really difficult, you know, especially if you've got the scenario where, like on PC, who knows what the CPU and the GPU are. There could be any combination. On top of that, your target resolution could be varied. And then to cope with all that, you've got probably some different quality settings which switch off different modes and so on. So you've got all these permutations of different settings. and again, against the further permutations that your game content could be completely different for different scenarios. So it's really difficult to get your barrier placement perfect. And even if you do, say, get it perfect on say, console and then port it across to PC, because the hardware is different, the conditions are different, it's very difficult then to expect that to be perfectly synchronized on different hardware. So that's the challenge. So, as it turns out, there's pretty much a solution for the majority of this. It's a solved problem, believe it or not. And this is why we're talking about render graphs. So the whole idea is it's a really elegant way where we can look at the global picture of the frame, figure out what all the dependencies are of all the resources in some sort of like directed graph, and then based on that, we can then go off and build our command buffers, but for each command buffer, we know exactly what the state of the resources will be. So for example, for the blue workload, well, my graph has already figured this out. It already knows that it's dependent on the other two resources, so it can set the perfect states for that. So there we are. We've solved the problem. But the thing is, so this was a solved problem back in about 2016, 2017. There were a couple of sort of major game developers that said, this is how we have solved this problem. We have got like a render graph system. But then I'm still here in 2023 saying there's loads of barrier problems in games, and we're not scheduling work onto the machine as efficiently as we could. So there's a bunch of reasons for this. One is just, it's a huge amount of work just to down tools and then port to a completely different kind of architecture, essentially. And if you were to go down like the path of implementing a sort of render graph, it can be very difficult to then port that to other games or different engines and so on. So it's a really sort of difficult thing to get into and then to port into other titles. So we're kind of stuck here where we are. So just to look at, in terms of the size of the problem, which is kind of interesting. So what we've done, we've looked at a bunch of different AAA games, so about 50 of them, and we've taken sort of render doc or pix captures and just had a bit of a survey as to what they do. And in terms of the number of resources that are written in a frame, like even though the draw call count might be tens of thousands of draw calls, actually the number of resources written is kind of in the order of like, it's low hundreds. And you think about it in terms of like render passes being nodes. So where you might have multiple resources written at one time, but then you might have multiple draw calls writing to that resource. Kind of the node count of a game, it kind of never really goes above 1,000. And it's still kind of typically low hundreds. So it seems like a sort of a graph solution is certainly achievable here. So what we want to do is come up with some kind of render graph solution that just makes the barrier to entry for render graphs much easier. So it gives you out of the box great sort of scheduling of resources, perfect sort of barrier placement, or as close to it as possible. And then it should be, once everything's broken up into these nodes, it should be easier to move them around and share the code around as you see fit. Kind of goes back to this original metric of how good your game architecture is. Like RPS will give you that sort of one-line change to move one pass before another. It kind of becomes trivial, so that's kind of exciting. And sometimes when you've got an abstraction or another system, you sometimes lose optimization just because you lose the intents of what you're trying to do through the abstraction. So we want to avoid that. We want to keep as much of the intention of the original game right down to the DirectX 12 or Vulkan layer, so we're not losing any sort of domain-specific optimizations. That's kind of important. And then, like a bonus, probably not a good reason to port to RPS, but it does massively reduce the number of lines of code in your engine. So as someone, I can testify to this, that I ripped out a few hundred lines of my buggy barrier detection code and put RPS in, and my game sort of ran faster. And so that was great. That's kind of cathartic to do all that. In terms of the SDK itself, it's kind of split into 3 bits. The first bit is like your front end. So to describe the render graph, we've come up with this language called RPSL. It's very much like HLSL. It's familiar stuff, and it even uses the DXC compiler, it's like a modified version of that. And it basically outputs like .c sort of modules. But we don't want to tie you into that. You can always use your own custom front end if you've got your own vision on how you want to represent a render graph. You can do that, or you can just build the render graph yourself with like direct C, sort of the API that we supply there. But the RPSL, it kind of looks familiar. So the first thing is you need to declare nodes, and these are kind of using that node keyword, and these will relate to C++ side callbacks which match those nodes. And you can kind of see that we've got these attributes that you tag to the resources, the parameters, and these will tell you what that kind of resource will be used for. You can kind of see how the render graph's going to now kind of work out the dependencies based on those. And you can, for render targets, you can specify where they get bound, which slot. And then you've got entry points into the RPSL, and you can have multiple of these. But here we've got like this export keyword, and we're taking in probably the only render target that you will explicitly create yourself, and that's the swap chain. So we pass that in, and then from there we can actually interrogate the resource itself, like figure out what format and size it is, and then we can go about creating transient resources inside the RPSL. So here we've created like an off-screen render target. And then there's a bunch of built-in nodes in RPSL. So the clear node, for example, it does exactly what you'd expect it to do. And then we can start calling our user-defined callbacks. So what we're doing here, we're actually rendering to this user-created off-screen target. We're going to render a triangle to it. Well, that's what you'd expect it to do. And then we're going to send it on to the next node, but this time that render target with the triangle rendered to it, that's the input for this upscaling node, which blitz to the back buffer. So that's basically as simple as RPSL gets. And like the output is basically sort of DXIL. There's a bit of sort of custom metadata to it, but it's kind of familiar stuff. And then you've got the runtime part of it. So this is where, because you want to have flow control in your graph, you want to be able to pass variables in to control for loops and if statements and so on. So these go in, and then we can start compiling the render graph into some meaningful thing. So this is the kind of output that it starts to generate. Firstly, it identifies all your resources, and then it identifies the barriers, and then the actual nodes which do work. And then you've got this kind of compiler which compiles the graph down to find out the most sort of efficient solution. So yeah, here we go. So these T underscore things, these are the barriers, and it basically sort of builds like a DAG of your dependencies. And this is again like a sort of typical AAA game where we've extracted all the dependencies and run it through, and this is essentially what you've got here. So the blue is the traditional vertex and pixel shader workloads. The orange is compute-based stuff, and then you've got the green are kind of like the copy and clear nodes. But the interesting thing here is, actually, first off, you can see how we've picked something like RPSL, which is like a fairly familiar language. It's quite an elegant way to express a render graph rather than something like a drag and drop node with sort of wires connecting it. You can see how it'd be like a rat's nest really quickly. So that's probably not the way to go. It'd end up kind of looking like this. But hopefully you can see here that there's lots of opportunity for different scheduling options and lots of overlap of work. And then that kind of compilation, you've got sort of different ways to optimize your graph. You could sort of optimize it for minimum amount of barriers, or maybe minimum render target footprint. And you've got some quite explicit control over it as well. So you've got this sort of keyword so even if, say, for example, over here, you've got sort of node 1 and node 2, and at least by the graph's view, they're not necessarily dependent and don't need to be in that order, but you know that you want to keep them in that order. We do have this sort of keyword to kind of force the order to be sequential there. So that's useful as well. So after it's been kind of compiled down and hopefully kind of optimized as best possible, you can kind of see here how we've managed to batch all the transitions together into one. So that'll be one API call barrier submit. And then here, this is basically a load of geometry submitting nodes. So now there's no barriers in between this. We can just send all those draw calls all to the GPU, and hopefully we get some really nice overlap of work. And then something I've kind of haven't really talked about is the concept of kind of memory aliasing and the scope of your render targets. So the ones in grey here, these are render targets that are going to persist through the frame, either because they're kind of used from the start to the beginning of the frame, to the end of the frame, or you've marked them as persistent yourself because you know that they are temporal sort of resources that need to persist through frames. But actually, a lot of the render targets in your game are things like, say, the G buffer. You render to it, then you're going to read from it, and then once you've read from it, you kind of don't need to use that memory later on. So RPS can actually just use that, can reallocate that memory and sort of mark them as transient resources. So that's what the red ones are. That's just the scope of these kind of transient render targets. So up to this point, everything so far is API agnostic. And to keep it that way, we've got like a custom sort of, well, we've got like a back-end API. And we supply the DirectX 12 and the Vulkan, and actually the DirectX 11 one as well. We supply these backends for you, but there's nothing to stop you from writing your own as well, if you want. And then you've got your C++ engine side sort of callbacks which relate to those nodes. So, for example, going back to our original example, you've got like an upscale node which is declared in the RPSL. So it takes two arguments, like a render target and like a source texture to read. And then, actually, the first thing is in the C++, the arguments must match in order, but the first argument on the C++ side is the RPS context, as you'd expect. But after that, so the first argument here from the RPSL is the render target. Now, RPS actually binds that for you, so you don't really need to use it. You can opt out of that. You can bind it yourself if you really wanted to, and you do have access to that target, but RPS can bind it for you, so there's no need to use that one. And then the next one you receive as, well, there's different options here, and we'll talk about this later, but you can receive it as the raw descriptor handle. So you bind that, and away you go. So yeah, that's the SDK. You can grab it from GitHub now and play with it. You sort of you can open up the solution. There's a bunch of different projects in it to point you to some interesting ones. That the example we were looking at, that's the render to texture example. That's probably nice and simple, a good place to start. Then you've got something like the downsample code. That's interesting because it shows you some of the features of the RPSL. say, for example, if you've got an array of cube maps, and each cube map face has a full MIP chain, then this shows you kind of the semantics of how to actually access a particular MIP chain element in a cube map in an array. So that's kind of useful. We haven't really talked about multi-threading, but there's a good multi-threading example in the SDK. So say if you've got like 100 nodes and you've got 4 cores that you want to multi-thread your command buffer building onto, right? You could go down the route of just splitting those 4 cores, like each could do like a quarter of the nodes and record them on a command buffer each. That's fine, and the sample shows you that. But in practice, some nodes are just 1 draw call, and some nodes might be something like the gbuffer, which is 10,000 draw calls, or a shadow map, which is 5,000 draw calls. So for those, you potentially want to then record those onto multiple command buffers and go wide, record those on multiple threads. So this sample shows you how to do both methods. That's kind of worth a look. And then there's like a really simple triangle sample which shows you the RPSL, but it also shows you how to do the same thing in the equivalent C API. So if you really did want your own custom front end, that's probably a good place to look. So yeah, let's look at some results now. So here's another RGP trace. Now, if I was to see this on my desk, I'd look at it and be fairly happy with it. It looks good. It looks pretty well optimized. Someone's loved this and given it some optimization already. It looks great. But what we've done here, we've taken like a render doc or pix trace off this game, run it through RGP, and then spat out the results and reanalyzed it in RGP, and then looked at the results. So probably first thing to notice is there's like a 0.7 millisecond win there, so that's great. Digging into it, you can kind of see it's reordered the passes around to what it thinks is a better solution. And actually, if you kind of zoom in a bit more, you can see how now you've got loads of overlap between the compute work and the pixel shader work. It's looking really nice. Even this surprised me a bit. So here in the geometry passes, so this is shadow maps and gbuffer here. Again, it's split out the barriers, batched them all up, and you can see actually there's quite a saving here as well. It's rather nice. Here's a predominantly compute-based game title. Again, there's a decent saving here just from reordering the passes, sort of reconfiguring the barriers. Kind of the opposite kind of flavor of game. This is all pixel shader work. No compute work at all, but it doesn't matter, does it? Because it's still just work on the GPU, and it's reordered some of the passes, batched up some of the barriers. So again, looking good. So this is interesting. This is showing you the reduction in number of barriers, which kind of suggests that most games, even if they've got some sort of auto detection of and auto scheduling of barriers, you can probably get it down to about half of that with a render graph. In terms of actual frame time improvement or frame time reduction, that's kind of important. We're doing all right here. We've got sort of, at the top end, it's quite extreme, but yeah, sort of, a decent few percentage speed up. We've got some interesting outliers here where actually RPS has somehow managed to make the game slower. And I think what's going on here is because we've extracted the game from a frame debugger, some of these games might have resources that are bound which are not real dependencies. So if you've got a UAV bound for loads of passes, it's going to detect that as a dependency, which it doesn't need to. So that's probably what's going on here. In terms of the memory footprint, again, because now we can alias a lot of the memory of the render targets, we're seeing like about sort of 50% sort of memory reduction, which is great. And then in terms of the CPU cost, because realistically you probably want to recompile your frame graph every frame, just based on various different things happening in your game engine. So you probably want to rebuild the graph each time. It's kind of still reasonable, you know, especially if you're multi-threading your game. Kind of typically no more than a millisecond, which seems reasonable. So, in terms of integration strategy, this is kind of interesting. So, the SDK samples that you will see, and certainly the sample code I showed you, goes for this kind of low-level approach, where in your engine callbacks, we're actually passing in the raw DirectX or Vulkan kind of views or descriptors. That might work for you, but I suspect you've got some sort of abstraction layer for your renderer in your engine. So you've kind of got sort of two options as I see it. One is to keep the RPS arguments abstracted, so you've still got your sort of node callbacks above the engine abstraction level, and then in your sort of API RHI layer, you can then actually get the raw descriptors as indices. That works. That's what I've done in my personal project. That kind of works well. Or you can just write your own RHI backend. That's another valid alternative. And probably worth pointing out that you don't need to go and just blanket port your engine to RPS, although long term that's probably a good strategy. You could always sort of dip your toe in the water and just try a certain area of your game. Like I'd probably suggest something like the post-process system, where you could just try it out, see how it's working for you. It'd be an interesting test. Right, so, okay, so as it stands, RPS it's out in the wild, it's on GitHub, it's all open source, and it gives you this nice sort of package of sort of your render graph solution. It'll manage your barriers, your resource scheduling, and so on. And it does multiple queue submission. It's fairly fully featured already. And very recently, we've actually added a bunch of nice tutorials on GPU Open as well. So in terms of next steps, well, now it's out in the wild. We're getting feedback both internally and from the wider community, so that's great. So we're always iterating on that. And we've got our own sort of AMD GPU Open sort of SDK of samples, and we're going to be upgrading that to the latest sort of version of what we call Cauldron. So Cauldron 2 is going to be coming out, and we'll be looking at doing an RPS version of that. So that'll be certainly more non-trivial example of RPS. So that's probably worth a bit of a browse through when it comes out. And then also perhaps a bit more sort of fully featured things like the BVH building. We'll probably add native support in RPS as well. So thanks to the core RPS team, and thanks to anyone that's already had a look at it and given feedback. That's it's really appreciated. But yeah, thanks for listening. Yeah, thank you very much. Taking questions.
Yes, we have some time. Please come to the break. Okay.
Thank you for the talk. I have a couple of questions. So first, do I understand correctly that this is purely a software solution, or there is some hardware support to it? And second, how would you compare your RPS solution, say, with UE5 RDG?
Okay, yeah, so the first question is, is it software only? Yeah, it's very much, completely open source, and it just goes down to that sort of like custom back-end layer, and then, yeah, we've got your sort of back-end layer implementations for DirectX 12 and Vulkan, but there's no extra magic going on here. That's not to say, I mean, who knows what the future holds, but, you know, perhaps this could be something where more if it does move on to the GPU hardware, perhaps in the future, but that's very forward-looking. But right now, yeah, you can use our solution, or you can use this as inspiration for your own. It's just pure C++ and compilers and yeah, your own language. Yeah, and then how does it compare to the UE5
RDG, render graph?
The render graph, similar concept. I'm not very familiar with the UE5 one, but yeah, the intention I suspect is very much the same. You know, it's a hard problem trying to get the perfect scheduling of all your work onto the GPU, and it's only going to get more difficult.
Okay, and then one last one. Basically, for developers that have an access to dev kits, are you going to provide a version with the with a console support for the RPS?
I believe at least that's partially in the plan. Yes, but there's not much of a barrier there in the sense that it's all just C++. There's nothing non-standard here. You know, it wouldn't be a lot of work to write another very similar looking backend.
Right. Thank you very much.
You're welcome. Any more questions?
Yes.
Great.
Hello, Cyril from Matabu. So
Hi.
I have a question about the thing like latency. Let's say we have a very fast-paced shooting game, 60 FPS plus or even more, and what I don't want to do is basically to wait for the whole render pipeline to be built and then sent to the GPU, because I want to have the lowest latency as possible. So you know the players are branding on screens that has 6 milliseconds latency. So if I had 48 milliseconds, they will kill me. So I need to do it as fast as possible. So is this rendering pipeline shaders? Does it help with latency, for example, or is there any place? So how can I batch the things, right? So push the stuff, then do something on the CPU, push another stuff, and so on.
Yeah, great question. Okay, so yeah, you'd need to do the CPU bit to compile your render graph. Then you'd start to go off and have to build the command buffers, and perhaps maybe you'd want to actually be submitting work to the GPU as like execute command lists calls to feed the GPU as quickly as possible, and have no latency between the last frame. So that's already cleared out of the GPU, isn't it? And then there's nothing stopping you from doing that. Yeah, absolutely. In terms of a scenario that we've tried out with RPS, we haven't really thought about it much, because most games do tend to buffer a couple of frames. But it's something we have looked at in the past, not necessarily for RPS, but just for virtual reality stuff, where the latency we needed to get right down. I don't think there's anything stopping you in RPS here, and potentially, it could make your life easier, perhaps. We'd have to have a look at that.
Okay, so it will help me with the barriers, but the rest I will need to do myself.
Potentially, yes. You might have to somehow massage your... I mean, it might help in terms of the organization of your game. You know, perhaps because there are certain periods where you've got the essential game content which you have to schedule in and have to present it. Other things might not have that sort of present interval sort of granularity. Maybe you want stuff which does run longer, perhaps persists through many frames, and perhaps, I think RPS could be a good way to express that, perhaps.
Okay, thank you.
Yeah, but great sort of line of research, and perhaps we should look into that.
Hi.
Hi.
I have just one question. So if I were to download the SDK, I just went on GitHub and saw an issue that someone tried to build it on Linux. Is it possible to run it on Linux and to play with it on Linux, or is it only Windows-only APIs and just locked in on Windows?
Good question. Off the top of my head, I don't know. I don't have a Linux box. I've never tried it. The majority of the people we work with, like sort of 99%, are all Windows-based. But in theory, I mean, it's, again, there's no magic there. It's all CMake and C++. and we have the Vulkan backend.
And Vulkan, yes.
So
it should work, basically.
So if it doesn't work now, and yeah, I don't think we actively support Linux as a platform,
Yes.
but I don't think there's much of a barrier to make that happen.
Sure, thanks.
But yeah, you might have to do some of that yourself.
Yeah, I'll try maybe.
Hello.
Hello. That was interesting. A question: is there any control over how render graph your solution is compiled? I can imagine that you can compile against many scenarios, sometimes for performance, sometimes for memory. So, is there any other way other than just changing the code?
Let me try and frantically scan back through my slides and show you the bit where this bit. So you've got some control, yeah. So out of the box, you've got different sort of compiler sort of scheduler flags, just as a sanity check, really. There's one which just preserves the original order of the nodes. If you weren't to reschedule stuff, that's kind of good, like that keep program order. You've actually got one which is to randomize the order, like every frame, just for absolute bulletproof testing of the dependencies between everything. But you can ask it to sort of minimize barriers or minimize the amount of memory in flight. And then you've got this sort of explicit control here with that sort of semantic to try and force the ordering of a certain block.
Okay. And that's done by setting up a
this
number of flags?
This subgraph sequential thing, see there? So you can force two nodes to be in a specific order. So even if the render graph goes, well, okay, I could reorder these. If you know that there is some internal dependency in your engine where you want to do this one, then that one, we can force that to happen. I think that's certainly all the control I've ever needed to use. If there is more explicit control you want, then we can look at making that happen.
Okay. Thank you.
Does that answer your question?
Yes.
Great.
Thank you.
Do we have another question? Also, thank you, Gareth.
Thank you very much. Thank you.